As is always the case, once we learn a derivative, we automatically know of an antiderivative. And if you were to take the derivative of arc sine of u over a, where u is some variable expression in terms of x, and a is some constant, then it's not so hard to show that the derivative is u prime over the square root of a squared minus u squared, which means that if you take the antiderivative of that, then you're going to get back to arc sine of u over a. Notice that the u prime turns into a du, which kind of makes sense when you think about those are two different ways of talking about the derivative. And we can do a similar process for the arctangent. An interesting thing to note here is that there's an extra factor of a when you work this out. And I'll leave that to you to discover, but there is an extra factor of a here. So when you take the antiderivative of this fraction, if we don't have the a here, which we don't, then we have to divide it out on the other side. So notice that the 1 over a doesn't show up in the arcsine, but it does show up in the arctan when we're integrating. These are things you're going to want to memorize, but if you want to know why it shows up, then you're going to have to go through the process of taking the derivative and seeing that this particular derivative reduces to this. And that extra a, again, is a constant that can be divided out. And then likewise with the arcsecant, almost exactly the same. We have that extra factor of a on the top. So we have to divide that one out. That does not show up for arcsine, but it does show up for arctan, and it does show up for arcsecant. So things to be aware of. The other thing to note is that the absolute value can be transferred from the answer to the derivative to the answer of the antiderivative. But these are formulas that you're going to want to memorize because otherwise you're not going to be able to do problems that look like this. So we want to recognize, again, same pattern as we saw before, the square root of a constant minus a variable in the denominator. That's indicating we're probably looking at an arcsine. If you have the reverse and the variable comes first and the constant comes second, that's an indication that we're probably looking at the arcsecant. And then if we don't subtract, but rather add, and there's no square root between them or on top of the whole thing, then that would be an arctan problem. So these are all different rules that look similar, but they all have little variations. So definitely make sure that you practice these because they don't come so easy. All right, so let's take a look at this. The process here is going to be very similar to U substitution. In fact, we are going to do U substitution, but we also want to do an A substitution as well. Some people are going to say, I don't need to do the A's, I can do it in my head. Well, maybe you can, maybe you can't. I'm going to do it with writing out each value because once you pick the right values to substitute, then you're going to reduce your integral down to literally carbon copy either this or this or this with some sort of constant out front perhaps. Okay, but the constant out front doesn't matter. So as we do this, we're going to be rewriting these identities over and over and over again, and that'll help commit them to memory. So we've got a constant minus a variable inside the square root in the denominator. So that looks like an arcsine. The variable thing that we're squaring is 2x. The constant thing that we're squaring is 7, right? This is an a squared minus u squared problem. Now, if we're going to replace the 2x with a u, then we're changing this from a dx problem to a du problem. So just like we would in a regular u substitution problem, you have to take the derivative of this expression, don't skip this step, and figure out what dx is in terms of du. All right, so that means that we can rewrite this expression. We're going to rewrite this, the 3 is just a constant. In the denominator, instead of saying the square root of 49 minus 4x squared, we know that 49 is a squared. We know that 4x squared is 2x quantity squared. Whoops, so don't write 2x quantity squared, write u squared. It's the same thing as u squared. And then the dx is the same thing as du over 2. Okay, so that's our u substitution. The 3 on the top and the 2 on the bottom can get factored out. And then we're left with the du on the top and a square root of a squared minus u squared on the bottom. All right? And again, this integral, forgetting about the 3 halves, who cares about the 3 halves? this integral du over the square root of a squared minus u squared is carbon copy exactly what we see up here. So now we're going to go ahead and do the integration, but there's really not much to it because we just have it sitting there right in front of us. We have an arc sine of u over a. That's what our formula tells us, plus c. Notice that there's no 1 over a in this one because arc sine doesn't have a 1 over a in it. All right, so that's pretty much our final answer. We just need to substitute back in. So instead of u, we'll write the 2x that u equals, and instead of the a, we'll write the 7 that equals. And that would be your final answer. Now, this is one of my favorite things in the world about calculus. We take a look at this integral, and we take a look at this integral. They are nigh identical. We've got a 3 here, we've got a 3x here. That's the only change. But take a look at the process here. Suddenly, we're not talking about an inverse trig function anymore. No, we're not, because the derivative of the argument, the entire thing inside the square root, well, it doesn't equal 3x, but it's some sort of scalar factor of 3x. So don't forget those old rules that we used to have, right? If we saw this before we even knew anything about the inverse trig derivatives, we would probably just go ahead and, by default, just jump right into u equals 49 minus 4x squared. This is just a regular, traditional u substitution problem. So don't fall into the trap of thinking that everything is going to look exactly the same. A subtle change like this, the 3 versus the 3x, is going to completely change the process. So we'll still do the du over dx equals, in this case, negative 8x. And then we'll solve for dx, and we'll get du over negative 8x equals dx. And we don't have an a value to worry about on this one. So when we rewrite the integral, we still have the 3x on the top. Now we have the square root of u on the bottom. And then the dx gets replaced with du over negative 8x. All right? So the x over x, praise be, will be divided out. And all we've got to do is a very simple little integral, right? This 3 over 8, or 3 over negative 8, factors out. And the only thing that's left inside the integral is the u raised to the negative 1/2 du. Not a natural log problem, right? Because this is not raised to the negative 1. So just use the inverse power rule. So we've got that negative 3/8 that's still there. And then we've got u is going to be now raised to 1 bigger. So negative 1/2 plus 1 is 1/2. But don't forget to divide by that new exponent. So dividing by 1/2 is the same as multiplying by 2. And we're done, right? We just have to simplify this to negative 3/4 times u raised to the 1/2 is the square root of 49 minus 4x squared. And I find that kind of fantastic, that just that tiny little change by including an extra factor of x in the numerator right here completely changes the look of this problem. We've got inverse trig versus square root. Here we've got the 2x and the 7. Here the 2x and the 7 stay squared. There's a different coefficient. Everything about this is completely changed. So you can kind of see how that's going to affect your answer. So a lot of people are going to say, how do you know when you're going to use an inverse trig function versus not? Well, one answer is you just experiment and see where it takes you. Remember that when you do this substitution and you're left with exactly the derivative, the integral that we know how to deal with from this formula from up at the top of this section, how'd that 2 get moved? The joys of working with OneNote. As soon as we see this integral that we recognize as something we have memorized, then we just apply it. Now, if we tried that same process over here, notice that that x wouldn't have gone away. We would have had an x times du over all of this stuff. And if the x doesn't go away, then we've got problems. We don't want a mix of u's and x's. So if we can get rid of all of the x's and replace them all with u's, then great. And the key here is that when we look at the thing inside the square root, the radicand here, the 49 minus 4x squared, its derivative is linear. This numerator is linear. So we expect that that x is going to cancel out. So look for degree, look for patterns definitely practice this stuff, and you'll get better at it as time goes on.